Learn about recursive and explicit rules that govern how numbers change, step by step. Explore arithmetic and geometric sequences. See how a constant difference or ratio shapes predictable number patterns. The limit. Where do sequences lead? Understand convergence and divergence, predicting the ultimate behavior of numbers. Explore how sequences reveal long-term numerical behavior, showing trends and stability. Understand their convergence towards a specific value, the limit. Divergent sequences grow infinitely large or small, never settling. This highlights unbounded growth or decay, a critical contrast to convergent sequences. Oscillating sequences unpredictably jump between values. They exhibit fluctuating behavior without direction, crucial for understanding chaotic systems. The concept of the limit is foundational, defining stability and predictability in number sequences, essential for calculus and advanced mathematics. Did you know? Some sequences grow so fast, they achieve infinity in mere steps. It's like a rocket accelerating beyond imagination. Surprisingly, some oscillating sequences never settle. They dance back and forth indefinitely, a perpetual motion of numbers without a final destination. A fascinating fact, some number sequences converge to a limit, essentially arriving at a single, stable value after an infinite journey. Consider the bounded but not convergent sequences. They wiggle within a range, showing patterns but never quite deciding on a single endpoint. Imagine tracking stock prices over time. Arithmetic and geometric sequences model this real-world financial growth and decay. Witness population growth. Sequences show how communities expand over generations, with limits predicting future carrying capacities. Explore radioactive decay. Exponential sequences model this, showing how much material remains after specific time intervals. Understand compound interest. Geometric sequences show how investments grow exponentially, empowering better financial planning for the future. Understanding sequence limits unlocks predicting long-term trends, crucial for fields from finance to physics, revealing hidden patterns in data. The concept of limits in sequences is fundamental for understanding convergence and divergence, shaping how we analyze iterative processes. Exploring the nuances of limits reveals how sequences behave infinitely, offering insights into mathematical structures and theoretical applications. Mastering sequence limits provides a powerful framework for problem solving, enabling students to tackle complex mathematical challenges with confidence. Sequences show numbers evolving over time, revealing predictable patterns governed by mathematical rules, crucial for understanding long-term trends. Arithmetic and geometric sequences provide foundational models for predictable growth or decline, illustrating constant differences or ratios. Limits describe the ultimate value a sequence approaches, essential for understanding long-term behavior and stability. Understanding sequence variation and limits allows students to predict system behavior and analyze trends in diverse fields. Looking ahead, understanding long-term trends in number sequences is key. This unlocks predictions for market behavior and technological advancements. Emerging patterns will drive innovation in AI and algorithms. Mastering these sequences means being at the forefront of technological evolution. Financial modeling will become more sophisticated. Understanding long-term number growth allows for better investment strategies and economic forecasting. This knowledge empowers smarter decision-making in science, engineering, and even personal finance. Embrace the power of long-term numerical understanding. In North America, sequences are often introduced with practical, real-world examples. Think population growth or compound interest. In Europe, the focus is often on rigorous theoretical foundations and abstract mathematical properties, emphasizing structure and logic. In Asia, there's a strong emphasis on computational approaches and algorithms, finding patterns through large-scale data analysis. In many African educational systems, sequences are integrated into applied mathematics, focusing on problem-solving and tangible outcomes. Myth: sequence limits always exist. Fact: some sequences don't settle down, they diverge to infinity. This is key to understanding long-term behavior. Myth: all decreasing sequences converge. Fact: they can converge to a limit, but some diverge to negative infinity if they never stop decreasing. Myth: numerical sequences are just about finding endpoints. Fact: they are powerful tools to model real-world changes, like population growth or cooling. Myth: numerical sequences are static. Fact: they represent a dynamic process where values change predictably, often revealing underlying patterns and trends. Observe how sequences evolve with strict mathematical rules. Understand long-term number behavior, variations, and their limits, building a strong foundation. Explore mathematical variations within sequences. See how numbers change predictably, laying the groundwork for understanding their ultimate long-term trajectory. Grasp the concept of limits in numerical sequences. Discover how numbers behave as they progress infinitely, revealing their final, stable numerical state. Visualize the long-term behavior of sequences. See how numerical patterns converge or diverge, illustrating their ultimate mathematical destiny. Did you know? Some infinite sequences don't just grow, they can actually predict the future. Their limits reveal long-term trends. Astonishingly, even seemingly random numbers can follow strict mathematical rules. Understanding sequence limits reveals hidden patterns. Counterintuitive fact: the most predictable long-term behavior can arise from simple, iterative mathematical steps. It's surprising, but sequences reaching a limit mean their behavior stabilizes, offering a definitive end-state prediction. Witnessed in finance, sequences show stock growth over time, revealing trends based on mathematical rules for long-term predictability. In biology, population growth often follows sequences. Understanding long-term limits helps us predict species sustainability and manage engineering utilizes sequences for structural integrity, calculating stress and strain over time to ensure long-term safety and performance of bridges. In computer science, algorithms evolve over time. Analyzing sequences helps predict performance, optimize processes, and ensure efficient long-term. Discover how sequences reveal patterns in number evolution, proving mathematics isn't static, but a dynamic study of change and long-term behavior. Examine the concept of limits, where sequences converge towards a specific value, showcasing the predictable end state of a mathematical progression. Explore divergence, where sequences infinitely grow or shrink, illustrating unbounded behavior and proving not all numerical paths lead to a stable conclusion. Delve into arithmetic and geometric sequences, the foundational models for linear growth and exponential change, predicting future values based on defined rules. Historically, sequences were first explored for their practical use in finance and astronomy, laying groundwork for modern analysis. Early mathematicians like Fibonacci and Euler pioneered sequence theory, linking them to geometric series and the birth of calculus. The 20th century saw sequences formalized in computer science, crucial for algorithms, data structures, and understanding computational complexity. Today, sequences are fundamental in AI and machine learning, modeling data trends and predicting future outcomes with remarkable accuracy. Mastering number sequences unveils predictable patterns, vital for long-term trend analysis and forecasting future values. Understanding limits allows us to analyze the ultimate behavior of sequences, revealing convergence or divergence with precision. Mathematical rules are the engine driving number evolution. They ensure predictable progression and form the basis of complex calculations. Sequence lessons empower students to grasp numerical evolution, fostering a sharp understanding of long-term trends and mathematical behaviors. Unlock the secrets of number sequences. Discover how math dictates their evolution and predicts long-term behavior. Let's dive in. What defines a sequence?